Good midday, ladies and gentlemen. Normally at this time of the conference, nobody really wants to listen to invited lectures anymore because in thoughts, he or she is already on the social part of the conference, on the excursion. But today, for sure, it's different. Everybody wants to stay here in the hall and will not leave it. When we look out with this windy weather and cold weather, nobody really wants to go on a ship or on a mountain. So I'm very glad that I have the pleasure to introduce our invited speaker, François Maréchal. I give a bit of information on his person. François Maréchal holds a process engineering degree and also a PhD degree from University of Liège in Belgium. In 2001, he moved to École Polytechnique Fédérale de Lausanne in Switzerland, where he joined the Industrial Energy Systems Laboratory. He is a professor heading the Industrial Process and Energy Systems Engineering Group, and he is conducting research in the field of process and energy systems engineering for the rational use of energy and resources, industrial processes, and energy systems. Maybe two more information. He is also editor of the open access journal Frontiers in Energy Research. And since short time, he also is chairing the energy section of European Federation of Chemical Engineers. And now we are happy to welcome François with his talk today on using CO2 and renewable energy for autonomous cities.
Okay, thank you for the introduction. I hope that the microphone works well. I will try not to move too much from the microphone. So I'm happy to be here after a hectic travel, but nevertheless, so I'm here, and I have a good news to you. If my system starts, okay. I have a good news to you. I'm pretty sure that we do not have any problem in energy. If we look at the amount of energy that we receive from the sun, in 1.5 hours, we receive enough energy to supply all the needs that we have for the whole year, which would mean also that in 1 year we receive enough energy to feed our energy need for 6,000 years. We could also say in another way, with only 0.1% of the surface covered by PV panels, we would then cover all the energy needs that we have. Okay, so this is the good news. The problem is that sun is stochastic and intermittent. Intermittent because there are the daily variations and the seasonal variations. And not all the people are equal in front of the sun. So if you go to Iceland or if you go to Colombia, you will not have the same solar irradiation. I have also another good news, is that Mother Nature is a very good process engineer. And Mother Nature has solved the problem of the intermittency and the stochasticity by storing the solar energy into hydrocarbons or carbohydrates, which is the biomass. And for doing this, it has established a process which is quite interesting, that is using catalysts, that is using carbon dioxide and water, plus nutrients, in order to create stored energy from the stochastic energy that it receives. And it has also introduced the circular economy, in a sense, because if you look at how we are, or the nature was using this trick, so from the solar energy, then you can have stored energy, which is stored in the biosphere, that is in form of carbohydrates, and then it supplies the energy by oxidation to the living animals. And the living animals are converting this energy and send back the raw materials for a new cycle. So this is quite interesting because then we can see that we have also the circular economy, which is then in place. Nature has also done something, is that it has taken a small, very, very small part of this energy that is stored in plants and has stored for the long term. And this is what we name fossil fuel. So if you look at the numbers, so over 100 million years, the Earth has stored 5% of the energy that is received by the sun in 1 year. Okay, and this is the fuel reserve that we have. And this fuel reserve, humans have realized that they were able to use it for their own purpose, being the living comfort, the mobility, and the production. So now it's important to see what are our needs. So I take the first part of the cycle. Using biomass, the nature has given us food, and food is allowing us to have the energy that we need every day to live. And everyone needs the equivalent of a quarter of a liter of gasoline per day just to supply our needs, to make our body operating. But we are not so efficient, so when we use this amount, we create waste. And we create organic waste, so the equivalent of 0.7 kilogram per day. Those are Swiss numbers. We produce this amount of bio-waste, and at the same time, we produce another quantity of waste, 2 kilograms in total per day. And this is just to operate our bodies. So, in fact, we need to operate our society, which means that we need to have the comfort, we need to have the mobility, and the industrial activities. So, for doing this, we need 5 liters per day of oil that we take in this nice reserve. Okay, so to be compared, so 5 liters with respect to 0.25, which is what we need for our body. And the consequence of using this resource is that we are going to burn the carbon dioxide, and well, we have the carbon dioxide emissions. Carbon dioxide emissions is 14 kilograms per person per day in Switzerland. Okay, if it would be a waste that you have to put in a garbage, each day you would have to carry 2 6-packs, more or less 2 6-packs of equivalent of in weight of waste to be put on the street and to be taken by a waste management system. Okay, so this is not necessarily the best thing we can do, and unfortunately, we do not see these 40 kilograms of carbon dioxide. So it disappears in the environment, and some consequences occur. So this is the climate change. So if we want to try to limit this element, so it would be perhaps nice we have to look at our energy system. So 47% of our energy consumption is in fact for our comfort, buildings, households, and services. And what you can see also is that, especially in Switzerland, most of those requirements are in the winter period. And this is important because, unfortunately, the sun is shining mainly in the summer. In addition to this 47%, we have 36% coming for the mobility, that we use for the mobility, and 17%, half in electricity and half in thermal needs for the industry. So industry is a little bit lower in Switzerland than other countries, but nevertheless we can consider this is representative. So if we now look at the 47%, most of these requirements are in cities. And cities have a characteristic is the density. So what you can see here, for example, in the city of Geneva, which is a small city compared to the size of the typical city in the world, but nevertheless, so 16 square meters of area are covered by 16 square meters of heated surfaces. Okay, so it means that this is a first dimension, so the density. They are consuming this amount of fuel and emitting 1 million tons a year by taking the mean value of Switzerland of carbon dioxide. They are producing waste, and they are receiving solar energy on the roofs. And if you look at the equivalent energy that they receive on the roof, so you can see that you have 3 times the amount of energy that you are spending as fuel today. So with our colleagues in the city of Geneva, so it was with the canton and with the service industriel, so the utilities, we have been asking ourselves, can we build a city that is autonomous in energy, which means that it would not emit carbon dioxide emissions. That means also that it would not import energy resources. But at the same time, we do not want to reconstruct the whole city, and we would like to make some profit because we were working with the utilities. So it means that we have to look at where we use the energy, and if you remember, most of the energy is used in heating buildings. And we do it in a very efficient way. So we take natural gas, we burn it in a boiler. Some people say that we go up to more than 100% efficiency if we use a condensing boiler. But nevertheless, so if we have a 90% efficiency for the boiler, we need 11 units of energy to supply 10 units of useful heat at 21 degrees C. So we do a very difficult exercise for the engineers. Have a fluid that is at 1000 degrees C to heat a volume of air at 121 degrees C. So a very challenging task, okay? Very high efficiency. So now we can perhaps ask ourselves, what is the thermodynamics telling us for this? And we can ask Arnaud, who was a French engineer from not the last century, but the century before, who is telling us that for doing this job of heating something at 121 degrees C when the temperature outside is 0 degrees C, we need only 1 unit of electricity. The rest can be harvested in the environment. Okay? So this is something which is important because then we have to ask ourselves, so why do we use 11 units of energy while the thermodynamic is telling us that we need only 1? Okay? So, and in this case, in fact, we also do something which is important, is that we tap in the fossil reservoir, which is a very small amount that the Mother Nature has stored for us. Okay? So, and the solution is heat pumps. Okay? The heat pumps are not perfect, so we will not do the 1 unit, but 2 we can do. Okay? And it is proven that engineers are able to design systems that go to this level of efficiency. Now, something which is important here is that the formula includes the temperature at which we supply the heat. Even though we need the heat at 21 degrees C, we will have to be higher. And the best would be to go at the place where the heat is at the highest temperature in the environment. So it means that we have another challenge there because my city is really dense and I would like to find the right place to catch the energy from the environment. So the idea would be then instead of using a single heat pump at a single place, we could perhaps then divide the job into 2 parts. Let's first go to the environment and harvest the energy, and on the other hand, distribute the energy and then distribute it at the right temperature in the right building. Okay, so now I have a system that I'm going to divide into 2 parts, and the trick is the distribution. And for doing the distribution, then we are going to use carbon dioxide. Why do we use the carbon dioxide? It's mainly because at 17 degrees C and 50 bar, we can use the heat of vaporization. So it means constant temperature, no temperature glide. Okay? We can, if I have to supply heat in a building, I can use the gas state of the carbon dioxide at 17 degrees C, and I will condense it. And I will use a heat pump to satisfy exactly the exergy that the people need. So if you are heated with a low temperature heating system, you will pay less than if you are heated with a high temperature system. If I have to produce hot water, supercritical carbon dioxide is very nice because it creates a glide. In this case, it means that the heat pump will have even a higher efficiency. And there is another important element there, is that when I have to cool the building, in fact, what I can do is that I can use the liquid carbon dioxide that has been produced by the heat pump, and I can produce I can produce gas, vapor of carbon dioxide at the same temperature. And at 17 degrees C is chosen because this is the best, it is very good temperature to cool naturally, so that's free cooling buildings. And in this case, it's free cooling with a direct exchange between the people that needs to be cooled and the people that needs to be heated. So for example, if in a bank I have data centers that needs to be cooled, and if at the same time I have people that are in the office that needs to be heated, then I can make a very nice synergy. So what it means also is that I'm using the, the carbon dioxide as a way to exchange, to capture the environment. So normally what I would have done is that I would have taken a heat pump that was taking the heat in the environment to heat my building, and I would have used a heat exchanger to cool down my building and throw the heat away in the environment. Here I'm capturing the exchange, okay? And of course I have to make a balance, so I'm going to look at where I have rooms for harvesting the heat. For example, if I have a wastewater treatment plant, I can use the heat from the water that I'm going to release in order to produce my carbon dioxide in the vapor state. And I will use a heat pump to adapt the temperature and the pressure in this case. If I have a lake, I can use the heat from the lake. If I have geothermal wells, I can use the heat from the geothermal wells. Okay? And now it depends on the balance. So I can also then, if I'm in the summer, for example, take all the heat that has to be released, that is released by the buildings, and I can perhaps preheat my wells. Okay, so that I will be then using the heat in the winter again. So this is a very nice system that is balancing finally with the environment. And of course, the fact that I have tubes allows me to go at the right place at the right time, and I can play with the different sources that I have. Okay, and there is another advantage, is that carbon dioxide at 17 degrees C will never freeze. Okay, so it means that I do not have to drill. I can install pedestrian ways in which I will have the two tubes, and I can even make them prefabricated. Okay, so it means that I do not have to drill a lot of holes in the city in order to install my system. And the fact that it is using the heat of vaporization means it is also quite dense, which means that the size of the tubes are much smaller. So this is the difference between tubes. Those are the tubes if I'm using water with a temperature glide, and this is the size of the tubes. Sorry, I'm losing sometimes the connection. Okay, this is the size of the tube, the smaller one, if I'm using the carbon dioxide. Okay, so now what is the benefit? So we have been working with the city of Geneva. We took the city center of Geneva. It was a district with that has this. So each square is 5 megawatt hour of energy requirement, and they consume the equivalent of 12 units of this 5 megawatt hour for the whole system. What you can see is that it's mainly heating during the winter and cooling during the summer, which means also that they consume electricity for the air conditioning units in the summer. If we then apply the carbon dioxide network, what we can see is that we have a factor 6 reduction in the energy consumption. So we go from, we have 84% reduction of the carbon dioxide, of the fuel usage, in fact, 100% of the fuel usage. And the only difference that I can see here is that I'm using the same amount of electricity, but instead of using this electricity in the summer, I'm using it in the winter. Okay? Now, typically, I have there one question. This will cost much too much. Okay? And the reality, we have made the analysis. Something which is important is that in reality, we are using existing technologies. The heat pumps exist today. I'm installing heat pumps in every building. So each one is free to choose the technology that he wants, and he will pay only the amount that it needs. So if it means that the one who is at a lower temperature is going to pay less than the one that is at higher temperature. While if you look at the district heating system, the one that is at the highest temperature is imposing the cost to all the others, right? In this case, each one pays exactly what it needs, right? And in addition to this, what we discover by doing the comparison between the present situation and the future with the district network is that most of the time the people do not count the cost of the air conditioning unit in the cost of the energy system. They buy it with the building, and then they forget that they have to refurbish or to replace the equipment. So what we have shown is that there was, in this case, a break-even after 5 years, and at the end we were really beneficial with this system, while in reality the conventional system is not paying off, so there is no break-even. Okay, so it means that the system is the good one. Now, one problem remains. I have to produce electricity in the winter, and people will say that you are going to buy electricity from Germany in Switzerland during the winter period, because our dams are empty, so we do not have the hydropower, and we have decided to phase out nuclear. Okay, so it means that during the winter period, most probably you will buy the coal power from Germany. In this case, of course, I lose the advantage because of the efficiency of the electricity production. But of course, I could use more sophisticated systems. So I could buy, for example, a combined cycle using gas, and then in this case, I will become more efficient. I could also perhaps use renewable energy, and this is what I'm going to do. So I'm going to use the PV panels to supply the electricity that is available to drive my heat pumps, right? And I will show you how it balances. And I can also, if the sun is not available, use fuel cells. And there I would like to introduce you a technology that we have developed together with my colleagues, which is a fuel cell, but it's not only a fuel cell, it's a fuel cell system. It's a fuel cell system in which you have air and methane that is entering, that is preheated. There is a fuel processing here, which is in fact reforming the methane with water in order to produce hydrogen here. The hydrogen is then put into a solid oxide fuel cell in which the oxygen from the air is going to go to oxidize the fluid and produce electricity. The conversion is 95%, so it means that I need still to, there is still a possibility of doing a post-combustion, and I'm going to do it with pure oxygen. The reason for this is that now I will have carbon dioxide and water here, and at high temperature. Then I'm going to expand it in a turbine, going into sub-atmospheric conditions, and here I have water and carbon dioxide at 25 degrees C, so I'm condensing water, separating the water here, and recycling it, in fact, here, right? And partly, of course, I have to close my mass balance. And then the carbon dioxide will then be compressed with, so it means that it is going to consume the part of the mechanical power produced here, and I will then have the possibility of having pure carbon dioxide that I can use in my network. Okay, so now I can send back, so if I have in one house such technology, I can send back the carbon dioxide to, in the system. I can, of course, use the waste heat of the conversion for heating the building, and the rest I can also use to evaporate carbon dioxide at 17 degrees C. So I'm going to use the overall amount of energy that is available, and I'm using the higher heating value here because I'm condensing water, right? The efficiency of the system is 80%, and the trick is because I'm doing a heat integration. So I'm reusing the entropic losses of the fuel cell to heat the system. In fact, it is heating the fuel processing that is endothermic, and which allows me to have more water sucked here. And more water means more hydrogen here, okay? That is then oxidized in the fuel cell. So the overall efficiency is 80%. 80% electrical efficiency with CO2 capture, and still 20% of heat available for either direct supply or for the district heating network. So this is the trick. This is one of the tricks. Another trick which is interesting is the use of waste heat. And in cities, we have always a very nice source of waste heat, which is the waste incineration. So if I'm looking at the amount of energy that I have in a waste incineration, so I have taken here 9 units of heat, I can convert it into electricity with a 30% efficiency, especially if I have a very good cooling source, and I have the carbon dioxide. It's a very nice cooling source at 17 degrees C. So the 30% I can do it. Okay. Now I have another dimension here, is that typically the district heating system is using the incineration is the whole year, but we are going to use only part during the winter period to heat the people, and the rest we have to nevertheless throw in the environment. So I have to look at what is the balance between the winter and the summer day. So what I'm going to do is that in the summer I'm going to produce electricity and I'm going to store it, and storing means a reduction of the efficiency. I will show you the technique that I'm using for this in a moment. But nevertheless, so now I have those units of electricity. I can use those electricity in the heat pump in my CO2 system, so I'm using the electricity. I can therefore harvest the heat from my heating system, which is at 17 degrees C, so it can be used, okay? And I'm just using the electricity to raise the temperature level. But the advantage of this is that I'm producing more electricity than the amount that is needed to raise the temperature level of the district of the waste incineration, which means that I will harvest heat in the environment. So now what is interesting here is that the same amount of heat that was available from the waste incineration is going to deliver 2.6 times more useful heat for the city. And in addition to this, the people who operate the plant do not have to take care, to consider the demand of the city. They just have to produce electricity. Okay, so it's a very important dimension. So now I have a system. I have a system in which I have my heat pumps in buildings, I have free cooling in buildings, I have refrigeration if I have a shopping mall, for example. I can also use the carbon dioxide as a very nice cooling source for the shopping malls. I have the heat recovery that is going to supply me some electricity. I have the balancing unit that is taking the heat at the place in the environment with the best temperature identified. And of course, I can add PV on all my roofs, okay? So that is going to produce electricity, and I'm going to balance with my fuel cell. Still, methane is not from renewable energy sources, which means that I will have some carbon dioxide emissions, okay? And then I have to see what we are doing now. So today, we are taking the treasure of the Mother Nature, and we are burning it to produce carbon dioxide, okay? But there is also a bank account that is filled every day, so which are the renewable energy sources. So I'm going to look at all those renewable energy sources. So for example, biomass. Biomass, I can convert biomass into natural gas, and I can use natural gas in my fuel cell. The natural gas is going to the conversion is exothermic. It supplies as well heat. So I'm going to connect my process to my district system so that I can also supply the heat when I need the heat. Otherwise, I will have a very nice source and I will evacuate the heat in the environment. Okay, this would be one solution. The other solution is the solar energy, with a big problem is the intermittency. So here, this is the energy consumption of Switzerland over the 1 year. If we apply the energy policy of the government. So what we can see is that in half of the electricity that will be produced by the photovoltaic panels will be in excess during the summer. And unfortunately, the German will do the same, and the Italian and the French as well. Okay, so we have a problem there. And then we have to remind us that nature has solved the problem. We can industrialize this process, okay? Industrialize the processes means that we can convert the sun into electricity using photovoltaic panels, and perhaps invert the process of the fuel cell. So this would be the reversible fuel cell. So it's a co-electrolysis in which I'm going to take carbon dioxide that I have to capture. It takes some heat for capturing carbon dioxide even from the atmosphere. But then I can produce methane that I can store in a liquid form and that I can distribute. I know how to distribute methane. So this is very important. So something which is important. So it's mimicking the artificial the photosynthesis, so it's an artificial photosynthesis, but the efficiency is 10 times higher than the photosynthesis. So it means that if you have an area to cover that is free, it's much better to cover it with PV panels than to develop energy cropping, okay? You would need 10 times more area if you want to do crops. Now, something that I can do now is to look at the whole system. So I need carbon dioxide, and I can make methane. And in the summer, in the winter, I will use this methane. I will go in the fuel cell, produce electricity for my heat pumps. I will reuse the heat of the conversion. I will even use the evaporation of the liquid methane in order to liquefy the carbon dioxide that will come back, okay? And I will reuse the waste heat at any time by exchanging with the carbon dioxide network. Okay, so now I have a very nice system because I'm now using the electricity that is produced in the winter, and I can use it in the summer in an efficient way, and with a distributed system. Which means that I have a complex system, and now it's time to make the balance. So what is happening for the whole city? Okay, I have to look at the amount of PV panel that I can install. I will have the waste that is produced by the people. I have the bio-waste that I can convert into methane. I have the fuel cell that is producing the carbon dioxide that I will reuse in the summer period. I have the heat that is supplied. I have the data centers that supply heat and consume electricity, the refrigeration, and I'm balancing with the environment. Okay? So if I'm comparing the situation there, if I'm looking at all the resources that I have, of course I have to invest in infrastructure. But what I can tell you is that I have enough energy to supply the whole city with all the needs that the city has in terms of electricity and heating and cooling. Okay? And if I'm doing the balance, I even have too much energy that I can export in form of methane, so in form of green stored energy, which is something which is very important. So it means that now for, let's say, the 47% of the energy consumption of Switzerland, I have solved the problem with my own resources. So it remains to solve the problem of cars, mobility, and industry. So let's look at mobility. So for the mobility, what we have done is the study we have made with Peugeot Citroën, in which we have designed a new car, which is in fact an electrical car, because we know that the electrical cars are much more efficient, but they have a problem. They need a very big battery if they want to have a long autonomy. So what we have built there is a car that is able to have an autonomy of 1,000 kilometers, okay? That is using a fuel cell as a range extender. So it means that the fuel cell, being informed about the distance you want to travel, will decide to start or not. And we use biogas as an energy resource, okay? So, and what you can see here is the design. So you can see that the battery is not so big. The electrical motor is big because we need power. The fuel cell is small. The fuel cell is small because we do not need the power, we need the energy. So we make it operate in a constant way. So we do not have to follow loads with the fuel cell because that's a battery that is going to do the job. And of course, I have to be informed. So it means that I have to be connected to the data grid to see where I want to go and to take the information from the GPS to know what will be the travel that we have to do so that I will be able to manage the system here. We try to show this here. So the energy given to the wheel the battery level and the fuel cell level. So the consumption is 1.1 liter for 100 kilometers. So if I was looking back to my previous consumptions, I was at 6 liters, so I can do a factor 5, right? And something which is important, the car is in the parking lots for 92% of its life. So why not use this fuel cell? The fuel cell has higher efficiency than the best combined cycle in the world today, okay? So why not use this fuel cell as a power plant? When the car is in parking lot, it is connected to the electrical grid, but then it can play in both directions. PV panels are producing, okay, give me the energy and I'm storing in my battery. The people need electricity, okay, I'm going to operate my fuel cell and I produce your electricity from biogas at a very nice efficiency, okay? The conditions is that I have to be connected to the information grid and I have to have a smart car that knows where the people need and when the people need their energy resources, okay? But nevertheless, in addition to this, I can connect the car to the carbon dioxide grid so that it can supply the carbon dioxide that I need to store the extra amount of PV panels that I will have in the summer. So it means that now the mobility problem is really solved. So instead of having the 10, I can say that I have only 3 needed in form of electricity and I know how to store it. Now the industry. The first thing that I will do is that I will increase the efficiency by doing process heat integration. And then I still have to supply a certain amount of heat. And then the trick is to use biomass. If you remember, I've said that you can convert biomass into natural gas with that is an exothermic process. So if you do a clever design of the conversion of biomass by gasification, methanation, and separation, you can harvest half of the waste heat at a temperature which is higher than 200 degrees C. So you can use it as a heat source for the industry. So it means that I would recommend to do a cogeneration units which are not producing electricity and heat from a given source, but that are going to use biomass to cogenerate fuel in form of natural gas and heat for the industry. Okay? In addition to this, what is important is that the biomass is a carbon hydrate. It means that it has oxygen in it. So if I'm just writing the mass balance, I will see that I have to find a way to have the oxygen leaving the system. And the oxygen is going to leave the system in form of carbon dioxide. Okay? There is a way to reduce this and to use it directly. So I can integrate the electrolysis in the system and produce hydrogen that is going to be combined with carbon dioxide in order to produce methane. Less carbon dioxide emitted and produce an increased production of methane, which is a biomethane because the carbon is coming from the biomass. Okay? And in this case, I can have a very nice system that can be used as well as a seasonal storage device. So new boilers that are becoming cogeneration units that produce stored energy and at the same time useful heat, which is in fact coming from the thermodynamic conversion. So it means that after having looked at the efficiency of the processes, I can also look at the efficiency of the conversion system. I'm going to produce synthetic natural gas out of the biomass and reusing the waste heat. And the synthetic natural gas that I have produced can be used in order to produce electricity and heat by cogeneration. So it means that I do not have only to have very big plants that convert biomass, but I can also have the distributed energy, which is the methane. Now it's time to make the balance, and still you can see that I'm missing some electricity there. Okay, but there is a source that I have not used. So I'm going to use the wind and hydro. And if I'm looking at the wind and hydro capacity potential that I have in Switzerland, in fact, I can supply all my electrical needs. Then I combine it with biomass that I have just identified. And what I can see then is that I have an excess of energy in form of electricity, and I have a very nice way to store it. So it means that I can sell it to the people that will need it at the time where they will need it. Okay, so now if I'm making the whole balance, I have the city that is also already a net exporter of carbon of biogas, and I have the industry and the mobility that is becoming a net exporter of energy in form of biogas. So it means that in reality, Switzerland can be autonomous in energy. It can even be a competitor to Russia in terms of producing natural gas. It would mean that we have to invert the direction of the tube, okay, because now we are going to feed the natural gas grid, and we will ask some people to deal with the management. So we need to have some storage capacities in the list. But Switzerland can become a net exporter of natural gas, of natural gas. So, what are my key messages there? It's important to look at efficiency first and not forget thermodynamics. Okay? The second message is that we have to look at systems, because that's from the systems dimension that we are able to identify the reuse of the waste heat somewhere. To some extent, I'm using, in this case, I'm mainly working with the waste heat that is released in the environment and trying not to release it in the environment unless if it is in a pipe. Okay? And yeah, don't forget the lessons of the nature as well. Thank you.
Thank you very much, François, for that interesting presentation and presentation of that novel concept. I wasn't able to get your vision in all its dimensions, and I think most of the audience wasn't able to follow it completely too. So I suppose there are many questions and good discussions we have in the next minutes. Yes, please.
This is Professor Birol Kilkis from Başkent University, Turkey. First of all, my special thanks and appreciation for bravely using some terms which are more or less taboo in the society. Exergy. I am grateful that you bravely use this word, which actually we don't have to use it, because it is just a simple matter of using the right energy resource at the right place, at the right order, and at the right time. So in this respect, my question is, you have opened our eyes to a large extent, but may I add one more step, if you don't mind? This is the low exergy buildings, because if you can, in such a city, maybe it's quite difficult, but if you can keep retrofitting these buildings also towards low exergy buildings, which means heating at low temperatures, cooling at higher temperatures, will be an additive contribution to the whole system, increasing the efficiency and increasing the COP of your heat pumps. Am I right? Or if you have any comments, I very much appreciate that. Thank you very much.
Yeah, I have two comments. In fact, the first one, by working with the Canton of Geneva, they have written exergy in the law. And they had to fight against the Microsoft corrector that was always changing an exergy into energy, right? But nevertheless, so it has been included in the law, and it has been voted and accepted by the people. I don't know if they have all read all the details, but at least it was in the votation, and it is really a law that has been validated by the citizens. And one of the reasons we did this is because it is very important to avoid develop infrastructures that do waste exergy. And one of the consequences is that the people in Geneva, when they do a development like a building, they have to show where they destroy energy. And the first element is the heat distribution system that goes into your direction. So think about the energy, the exergy that you need for distributing the energy. And this is, for example, to avoid people installing electrical heaters, okay, and push them towards floor heating. And then to think about, and I'm working in Singapore, because then it's a high temperature district cooling systems that have to be developed, or district cooling that has to be developed. And in this case, it's really think about what are really the needs. So do I need really to cool all this air to 6 degrees C to finally distribute it at 20 degrees C to have the comfort? And this is, I think, a very nice consequence, because then the exergy is really used by the engineers and the people that do develop. And they are forced to justify a reason why they would not use the best performing system that is in the list. Okay, so this is something which is very important. And then, of course, I'm using exergy in a very large extent everywhere, because the major energy supplier in my system is the environment. Okay, and exergy is exactly saying this. If you want to minimize the amount of energy that you need to supply a service, you have to tap in the environment. Okay, and the best way is to industrialize this. So go in and capture the heat or the colds from the environment.
I see some more questions here in front. First was here.
I am Cherry from the University of Roma. I wish to thank you for this thought-provoking presentation that is very interesting and will produce probably in the future many things. But before I ask you one question, may we go back to the Carnot cycle?
Yes.
Evaluations.
You want to take this one or the next?
The next one, but because Sadi Carnot is okay.
Or
Here,
or this one?
No, a little bit back.
The one back is this one.
Oh, the next one? Okay, that one. I find that with the 30 degrees against 0, the Carnot efficiency is 55. Should it be just 0.1?
Yeah, but so the efficiency that I'm writing...
I'm surprised.
So the efficiency that I'm writing there is, so it's the technical efficiency. So it's the difference between the real consumption, so the ratio between the real consumption and the theoretical one. Okay? So I have calculated the Carnot.
So the complexity, the efficiency is 5%.
So what I'm saying there is that if you calculate the minimum amount of mechanical power that is needing for driving this heat pump, the real one will be 50%. Will be twice the amount.
It's 5%.
No. It's the ratio between the.
I understand.
No, yeah. Let me just redefine it. So it's the ratio between the real consumption and the minimum one. It's just to indicate how good the technologies can be with respect to the best, the minimum thermodynamic.
I clearly understand. However, the Carnot efficiency in this case is 0.1. Next. And I also see that 30 degrees, 17 degrees, electric quantity percentage is 75%. It's an enormous quantity.
Yeah.
I agree with you. But wait a moment. Now I want to go to the last question. Yeah. Because if this very interesting system would be copied by all the cities in the world, all the families, and so on, I will push my family to try to go in this direction. So, what will occur to the surplus of methane that is produced by all the system? Because all the cities will produce a surplus of methane. We will eject the methane in the atmosphere, or what we have to do? That is, the methane is a very worst, very bad greenhouse gas.
So the reason why I can show that as I'm showing that the Switzerland can be a net exporter of methane means that we have degrees of freedom. Of course, it means also that I have installed too much solar panels. Because if I'm installing less solar panels, it will be, I will have a lower amount of methane production. So it's just and with respect to methane, in fact, we can, instead of producing methane, we can also produce methanol, DME, Fischer-Tropsch fuels, because I'm using a chemical reaction, a synthesis reaction. The reason why I'm using the methane is just because it's a distribution system that we have in Switzerland, okay? Now, with respect to the balance, it shows that we have degrees of freedom. And I was also expecting one question that was more or less related to the comment there, is that I have not changed the buildings. So in reality, if I can also study the increase of the efficiency of the buildings, and I have also to study the increase of the gray energy content in isolating buildings that are going to compromise with the energy that I'm harvesting, okay? Having said all this, at the end, it's just a question of engineering with a very intriguing question as a professor. Most of the technologies that I have presented there exist today on the market, okay? And my major difficulty is that if people decide today to develop a district heating system, with hot water, my next slot will be in 60 years. Okay, so which then says to professors, okay, we have to create engineers that are ready to take some risk, like the one that I'm showing here. And there is another paradigm. It is the fact that instead of having a centralized system, it's a decentralized system. So there will be heat pumps and/or cogeneration units in buildings, and it can be even a fleet of fuel cells that will be cars, and perhaps that in the future we are not going to be the owner of the cars. So perhaps it will be a fleet that will be piloted in a Uber type, where you will say, okay, I need a car to go to be at this place at this time. And the system will have to decide if the car is still going to supply power to the grid, or is going to take power from the grid because it is used as a battery, and if it is available, the nearest to you, to supply the service that you need. So the smart cities there will even be more important, because there will be a strong link between energy and the services that are related.
We have two more questions here in the front row from Yershi and Jean-Pascal. And I see more rising hands, but we are close to 1 o'clock. Okay. And then I would say we take one in the back.
Don't worry, I will not examine you from Carnot factor. My question is a little bit more about strategy. I've realized that your approach is very much different from the plenary speaker from Barcelona. You know, this French person who just believed in hydrogen and nothing else. I think your approach is much more realistic. You made some calculations about the car, which is interesting. But my question is, have you made at least basic economic assessment? If this is implemented, what might be the return? Because I've seen very, very nice studies from Austria self-sufficient region. Everything looked marvelous, just the economy. They've got about 50 years payback period.
Yeah, so perhaps first, the story of the car. So the study was done with Peugeot Citroën, and we have estimated the cost of the car using their standards, okay? And their answer was, if someone is supplying me, because I'm assemble cars, okay? If someone is supplying me with the fuel cell, then I will buy it, and this is the way to go. So, and this is part of the answer. Related to this, it's a question of the market, and there, chemical engineers are used to speak about the scaling factor. So the bigger, the cheaper, right? In the case that we are considering here, it's not the bigger the cheaper, is the highest number, the cheaper. So it means that to develop this system, in fact, we do not need people that do demonstration on small scales, but we need investors that are going to build the factories that are going to produce the units that we need. We need heat pumps, we need fuel cells, and they will become cheap if they are entering into the mass production. What I'm doing there with the car is that, in fact, the car is becoming the power plant. So I'm going into the market of the power plants. At the same time, I'm going to the market of the cars. And if you look at one of the emerging developer today is Elon Musk, and what is he doing? The gigafactories. So it means that he is using this trick. So if I want to reduce the cost, I have to enter into the mass production.
Jean-Pascal, please.
Jean-Pascal Van Ypersel, Université catholique de Louvain, Louvain-la-Neuve, Belgium. Thank you very much for your very interesting talk. I had two questions. One question has just been asked. So the other one is, did you also look at the energy return on investment of the system? I was in the same room here this morning hearing a talk saying that, for example, the energy return on investment of solar panels, PV panels, was very low, much lower than other techniques. Did you look at the energy return of the whole system you are suggesting? So, thank you very much.
We are doing a lot of life cycle analysis studies. One difficulty of all those studies is that the basis is the observed values that the market allows us to see. Okay, so it means if I want to see what is the environmental impact of a refinery, I have to have an oil producer that is going to publish his numbers. Okay, and this is the way the databases are produced. And with this respect, there is a big problem, is that I'm talking about future technologies. Okay, so it means that I cannot use the present technologies to penalize my future technologies, because the market of the technologies will also change, so their impact will also change. And then there is another important dimension, is renewable energy. So we did, for example, a study on what is the perfect isolation dimension of a building. So how many isolation we have to add in a building if the building is heated by a heat pump that has solar panels on the roof. Okay? And then you realize that if you do not use green sources to produce the isolation material, you stop isolating the house very quickly, okay? Because you do not see the effect of the advantage of increasing the efficiency, okay? So it means that I fully agree that the energy return has to be calculated, but in a holistic way, and considering that the renewable energy sources are limited in reality, because they are limited with the area that we have available. And this is something which is, at the end, very important.
Thank you. There was a question from the lady completely on the right.
Thank you for your presentation. I'm Laura Vanoli, University of Cassino. In your smart energy system, you take into account the use of fuel cell technology. But there are some problems about the use of this technology in terms of durability, reliability. So what do you think about the use of this technology and the development of this technology in the future? Thanks.
Yeah, so if you look at the fuel cell research community today, what they are looking for is reducing the cost by reducing the thickness of the membranes, for example, and increasing the lifetime. So those are the two main domain of research today. The third domain is the reversible one, so combining electrolysis and fuel and electricity production. Now, the system that we are proposing there, for example, will never be built as with conventional fuel cell manufacturers. And the reason for this is that if I want to be sure that it penetrates the market, it has to be cheap and produced in mass production. In order to reach this, then you have to go to, and what we are looking at is 3D printing. So can we print the heat exchanger system? Can we plug on this heat exchanger system the membrane? Which means that if a part is going to fail, if a module is going to fail, then you can replace it. And if you have mass production, then you will just take this, recycle it, and reproduce it. The fact that I'm also using it in a car rather than using it in a house is that the expected lifetime of a car is 7 years, while in a house it's 25 years. And so the difficulties that would arise will be different because the people will accept to have a shorter product lifetime, in fact. And I guess that this is the way we have to go. So some manufacturers, even today, with conventional fuel cells, provide you with the guarantee that they will replace the modules if they fail. And this is then really creating a new market strategy, in fact.
As long as we are waiting for Natasha to chair the award ceremony, we can let François working a bit more. No problem. And I've seen there is a question here in the center of the audience.
Thank you. Thank you, François, for this nice presentation with many insights. According to my view, in order to a city be self-sufficient, I think we should include also food. Have you thought about extending your approach, for example, from the respect of circular economy, urban farming seems to be very promising and that kind of things?
Yeah, so introducing the food has several dimensions. So the first one is that it is going to compete with the area that I'm using for the PV. Now there are new technologies that are coming into place, for example, the dye cells. And at least with one of my colleagues, we are working on choosing the right materials in the fuels, in the PV panels that would use only the part of the irradiation, of the solar irradiation, the wavelength, that will not be penalizing the food production. Okay, so you choose the material in order to take the part of the wavelength that the plants do not need, right? And then you can build greenhouses. The greenhouses can be heated by the carbon dioxide network if they need to be heated. So it means that you increase the production cycle. You can then have greenhouses that are going to co-generate electricity and food. Okay, and of course then you have also to have an integrated vision of the water usage. But I have a lot of networks available there. One of the tricks that we are also using, so that I have not presented here, is the way to convert food waste into natural gas by hydrothermal gasification under supercritical conditions. And if you do it like this, then you have the possibility of recovering the nutrients as well, so closing the nutrients balance at the same time. And in this case, then you also avoid using fossil fuels to produce fertilizers. So this is the overall vision. I think that the system people will always be will always be there to improve the overall efficiency. So I've said today we are able to reach 55% of the best. I hope that in 10 years I will be able to say 60, right? As soon as we see the benefits. So for the moment we have to make the first step from the natural gas boilers to the use of heat pumps. And as soon as the engineers will understand this step, then the next step is, of course, increase the efficiency of heat pumps. And you are also working with manufacturers of heat pumps to make them more efficient. Yeah.
I just have seen Natasha came back for the award ceremony, but let's close with a final question that was there on the right side in the center.
Thank you.
Yeah, thank you for your very challenging presentation. I have one question because I think many people will fear these large amounts of CO2. So did you carry out any safety impact study what would happen if one of the pipes would rupture? And probably if you use that on a large scale, that will happen. So what will be the impact in terms of victims, etc.?
Yeah, so in fact, we have made a complete study on the safety issues because as nobody was using this technology before, in order to build a pilot plan, we had to make the certification. And so the idea is the following, is that on the one hand, so there are two major risks. The first is the brutal rupture of the pipes. And in this case, the risk is that someone is just there and received carbonic snow flow and it will be then burned. So this is something that I would say we have to manage, and the idea would be, I've shown you the Pedersen pass, it would be to use a double pipe. The other risk is a small leakage inside the buildings. Okay, because in this case you could reach the brace limit, so you cannot you will reach the asphyxia limit. And in this case, what we do is that we have in fact made the district heating system has a grid that allows to detect the leakage, and that is going to close the part that are affected by the leakage, in such a way that, and the volume is calculated in such a way that the amount of carbon dioxide that is in this volume will not reach the asphyxia limit. And in this case, so we are safe. And I can even tell you that it works because we have had the experience. So we had a small leakage and the system has correctly stopped. So seems to be okay. And one other trick that we would like to use is, in fact, the refurbishment of existing district heating systems by retubing them. So you can put the tubes in the tube. And in this case, then you can handle the leakage in a much safer way.
So let's thank François once more.
Thank you.
And please don't leave the room. I will hand over now to Natasha for the award ceremony. If you will leave, you could miss to be awarded.
Good afternoon, distinguished guests and participants. It is my pleasure now to welcome you on the awarding session where we will present the awards to the best papers. I know that you are excited to hear who are our winners, and the poster evaluation have taken a little bit longer, but bear with us. First, we have to deliver the award to the most cited paper of the 7th SDEWES Conference, who was not able to be with us 2 days ago. Let me just be reminded about the content. With the dramatic decrease in the costs, the PV technology is making revolution today. And I know that the author of the most cited paper of 7th SDEWES Conference has done a lot of work in this area, even starting in 1990s. And in their paper published in the Energy Special Issues of the 2013, they call it Looming Revolution, predicting exactly what is happening today and how the photovoltaic technology will change the energy markets fundamentally. And this turned out to be the most cited paper of the 7th SDEWES Conference. Reinhard Haas, would you join me on the stage to accept your so richly deserved honor?
Thank you very much. It's really a great honor for me to get this prize. And it is also, I think, a reward to the research on the future of renewable energies. As I said in my presentation yesterday, it is important to provide, for example, right incentives for the integration of different types of the renewables. And in this paper, we have tried to sketch the frame, how this could happen in the future, and also how we could integrate even more variable renewable energy sources. Thank you, and I'm looking forward to the next presentations, also next SDEWES conferences, to continue this discussion. Thank you, Natasha.
Coming back to the best papers, let me just mention that the winners will be awarded with certificates from SDEWES, and an extra special thank you for us. They will also be awarded a book written by a member of the SDEWES International Scientific Committee. Now I would like to invite Peter Varbanov as the chair of Poster Evaluating Committee to deliver the awards.
Yeah.
Thank you, Natasha. It's a big pleasure to be the poster committee chair again for SDEWES. I've had the invaluable help of the committee members, Shil Kilkish, Antonio Piacentino, Oefi Foley, Chuang Wang. It's been a tough decision to make, especially the last 2 days. But we have finally made up our mind. We have decided to award for 3 excellent posters, but many others have been very good as well. Okay, so let's start with the third place. We have Chun Han Ko, phyto extraction by Taiwanese chenopod and napier grass for heavy metals and comparison with soil excavation by life cycle assessment for 2 contaminated sites. Yeah. My congratulations.
Thank you very much.
Okay.
Thank you.
Huh? Okay. Second best poster is Zafer Utlu. Okay, for the poster, fabrication of AAO templates using different heat storage capacity salts for thermal energy storage systems. Okay, please come. Ah, you're a replacement. Okay.
I will pay for you.
Of course. Fine. Congratulations.
Thank you very much. I am just taking this honor to receive the award on behalf of Zafer Utlu, my colleague. He just left because he has today a lecture in the evening in Istanbul, so he already left. So thank you so much.
Very good. Okay. We are coming to the best award, first best poster for Blanca Moreno. Okay. For the poster titled The Impact of Virtual Power Plant Technology Composition on Wholesale Electricity Prices, a comparative study of some European Union electricity markets. Blanca. Left? Left? Okay. Okay, somebody will come.
So coming back to best papers, let me first introduce the award committee members. Professor Jiří Jaromír Klemes, Professor Ingo Stadler, Professor Brian Wat-Mathiesen, and Professor Alexander Zidanšek, all members of the SDEWES International Scientific Committee. We really have had a difficult task, but also with help of the old editors and reviewers. Finally, I think that we managed to do a great job, and we have our 3 winners. The first one deals with artificial networks and applied to control lighting in buildings. The winning authors come from Italy, and I would like to invite Josefina Chula to receive this honor.
Thank you so much for the win. I'm very happy, and I wanted to thank the committee and the organization of the SDEWES Conference, and in particular my research group, and the Professor Beccali, my colleague Marina Bonomodo, and Professor Lobranol, and a PhD student, Michael Mradzek. Thank you so much.
The second best paper comes from Germany, and the authors show how to use European Thermal Atlas to identify local heat supply and demand. Bernd Müller, please join me at the stage to accept your award.
Thank you so much, Natasha. Thank you so much, dear committee. Thanks also extended to the rest of the SDEWES Conference, which really has shown again how smooth running a machine it is. I would like to thank my co-authors, in particular, Eva Wichers from Flensburg and Urban Persson from Halmstad University in Sweden. They have spent most of the summer really to make sure that we had the results that we presented yesterday. So thank you so much.
And the first best paper, again, comes from Germany. But this time we have excellent contribution towards optimization of energy systems in order to get them ready for power to hydrogen applications. Laura Welder, please come up at the stage to receive your award.
Yes, so I would also like to take the opportunity to, of course, thank my co-authors who did this paper together with me and contributed in all different manners. But beside this award, I would also like to thank the organizing committee for organizing such a wonderful event and giving me the opportunity to meet so many nice and inspiring people. Thank you.
And it is not the end. We have to present yet another award, this time for the most loyal participants to SDEWES Conference. Amela Ajanovic, please. She is the most loyal participant for this SDEWES Conference.
Thank you very much. It's always a pleasure to be here. I would like to thank the organizing committee. Thank you.
So coming to the end, I would like once again, on behalf of award committee, poster evaluating committee, all SDEWES members, and personally, of course, to congratulate all the awardees and express the deepest appreciations of this great success. Another round of applause, please. And before closing, I would like to ask all awardees, all members of the committees, to join us here at the stage for a joint photo. Please.
Yeah, totally. We need to turn it off.
Totally turn it off. Could you ask them to turn projector off? Yeah.
Congratulations for this session, very nice. Yeah, I think, I also agree with the selection. Okay. Well, yeah, we hope. Thank you. Yeah. Because, several the selections we thought maybe, well, based on a small comparison, maybe because we unfortunately have to rely upon the view of reviewers, which, well, not always so. Okay. Yeah, for me too. See you later.